problem number 5, 2857. A torque on a current loop. Let's set up again a right-handed coordinate system. Always right-handed. X, Y, Z. And we have a loop, rectangular loop, which comes off at an angle. And the angle is theta. It's hinging here, frictionless about the z-axis. This length is L1, and this length is L2. This is also L2, and this is also L1. And somehow, for reasons that are not explained, there is a current flowing in this direction, the same in this direction, and in this direction this current is I. We know the total mass of this whole thing because you're being told that the mass per unit length is 0.19 grams per centimeter. And you know L1 and L2, so you can calculate the mass of all this, of this whole thing. Now the force on each one of these individual wires in the presence of a magnetic field would be I times L cross B. And B is given, is in the plus Y direction, uniformly throughout. If you analyze the forces on each one of these 4 elements, and I would like you to do that on your own by carefully evaluating the direction of L cross B, L is always a little element in the direction of the current, so L dl would be here, and here dl would be there. Then you should be able to convince yourself that the force at the bottom here, on this part here, is in the x direction. I'll call it f of x. And therefore right here, it's the same in magnitude. I call it minus x, just to tell you in which direction it is. This wire here experiences a force in the plus z direction, and this one experiences a force in the minus z direction, and the two exactly cancel each other out. So I don't have to worry about these two. But these two do not cancel each other out. They do cancel each other out in terms of the sum of all forces being 0, but not the sum of all torques being 0. So there is a torque on this system. But yet, we know that it is in equilibrium. So the only way that it can be in equilibrium, that there is another torque, this is a counterclockwise torque, there has to be a clockwise torque to hold it in equilibrium. And so I'm going to now make a drawing from the side. I call this hinge point through which the z-axis goes P. This one is L1. This angle is theta. And I'm going to draw all the forces in there that I can think of. This is the total mass of the loop, mg. Here is that force Fx due to the magnetic field and the current. Well, there must be here this force minus x, right? I call it F minus x. It's the same in magnitude as this one. They cancel each other out. But since the sum of all forces must be 0, according to Newton, at this hinge point, there must also be a force mg up. And so you'll see now that the sum of all forces is now 0, but now the sum of all torques is also 0. It doesn't matter which point you take, whether you take this point, this point, this point, this point, this point, or this point, or this point, or this point, the sum of all torques will be 0. I might as well choose this point P. So I will calculate now for you the torque relative to point P, which must be 0. So when I'm here, there is no contribution to this force and this force. I have a clockwise contribution due to this one. So that is this arm times this force. Now the arm has a length 1/2 L1 times the sine of theta times mg. That is the clockwise one, I call this clockwise, must be equal to the counterclockwise, I give them both a positive sign, and the counterclockwise is relative to this point P, this distance times this force. And this distance is L1 cosine theta, L1 cosine theta times Fx. Notice I have one equation with one unknown, and that is Fx, because I know all the other things. L1 cancels, by the way. I know theta. But I also know that Fx equals I times L2, mind you, it is the length of this wire here, perpendicular to L1, times that magnetic field B, which is only in the y direction. I know the magnetic field, I know L2, I know, oh no, I know Fx, I know I, and I know L2, so out pops the magnetic field. So I can calculate the magnetic field. Interesting problem. So due to this magnetic field, this loop will come out, it will experience a torque, but the gravitational torque exactly balances it, and so it will be standing at equilibrium at this angle. And well, you can argue that if you increase the current, the angle will probably become larger, and if you increase the magnetic field, the angle will probably also become larger.